You've probably held one of these 1,000 times and never really given it a second thought. I'm talking about the humble aluminum beverage can. It feels simple, almost disposable. But if you look closer, and I mean really look closer, you'll find it's an absolute masterpiece of precision engineering. Seriously? Have you ever actually examined one? Every curve, every groove, the way that little tab opens? Well, as we're about to see, absolutely nothing on this thing is an accident. It's all part of a truly brilliant design. So here's how we're going to do this. We're going to break this can down piece by piece. First, we'll look at the big picture, then we'll zoom way in on its super thin walls. After that, we'll uncover the secret strength of its domed bottom, deconstruct the absolute genius of the lid, and then finally, we'll see how it all comes together. All right, section 1. Let's start with the can as a whole, because it isn't just a container. Not really. It's the end result of one of the fastest, most precise manufacturing processes on the entire planet. And this is the fundamental challenge for the engineers who design these things. Every single feature is a carefully calculated trade-off. They have to use the absolute minimum amount of metal possible to save money and weight while making darn sure the can is strong enough to hold all that fizzy liquid inside and survive the journey all the way to your hand. And they have to nail it at an unbelievable speed. Get this, a modern production line can churn out up to 3,000 cans every single minute. That's 50 cans a second. Just think about that. That scale demands a level of engineering perfection that is truly, truly mind-blowing. Okay, so now let's dig into the body of the can, because this is where you can really see that battle between strength and using less material play out in a super dramatic way. You see, the can body starts out as just a flat little disc of aluminum. It then goes through a process called drawn and wall ironed, or DWI. A punch smacks it into a shallow cup, and then a series of ironing rings press against that cup, literally stretching it upwards while thinning the walls out to their final, incredibly slender dimensions. And the craziest part? It's all from that one original piece of metal. The results of all that stretching and ironing is a wall that's only about 90 micrometers, or microns, thick. Now, I know that number probably doesn't mean much on its own, so let's put it into perspective. Let's see just how thin that actually is. A single strand of human hair is about 70 micrometers thick. So, yeah, the wall of this can, the only thing holding back all that pressure from your soda, is just a little bit thicker than a hair. That's the level of precision we are talking about. It's incredible. Okay, let's flip the can over and look at the bottom. Ever wonder why it isn't flat? I mean, a flat bottom seems like it would be way simpler to make, and it would make the can more stable, right? Well, it turns out a flat bottom would actually fail spectacularly. And the reason is all thanks to a classic physics principle, the arch. You know how an arch in a bridge distributes weight down to its supports? Well, the dome on the can's base does the exact same thing, just in 3 dimensions. See, if the bottom were flat, all that internal pressure, we're talking like 90 pounds per square inch, it would all push on the weakest point, right in the center. It would bulge out, and the can would just wobble all over the place. But the dome, it's clever. It takes all that force and redirects it outwards into the much stronger, much thicker part of the base, what's called the standing ring. This comment from a Reddit user just sums it up perfectly. It's such an elegant solution, right? It gives you immense strength while using the absolute minimum amount of metal. It's basically using geometry as a structural element. Just brilliant. So now, let's move on to what is, without a doubt, the most complex part of the entire can, the lid. The body and the base, remember, are one single piece. But this lid is a whole separate component, and believe me, it is packed with a shocking number of clever little innovations. Okay, so here are the basics. You've got the pull tab, that's your lever. It's attached by a rivet, that's your fulcrum. And when you pull it, it presses down and breaks a carefully machined score line, which opens the tear panel. Seems simple enough, right? Ah, but the real genius is always in the details. Now, some of you might remember the old pull tabs, the ones that came completely off the can. They were a huge litter problem and, honestly, a bit of a safety hazard. The modern stay-on tab was a total game changer, turning the tab into this clever 2-part lever system that actually stays with the can. But here is a detail that I can almost guarantee you have never, ever noticed. That little rivet holding the tab in place, it's not perfectly flat against the lid. It's actually manufactured to be tilted at a tiny angle, just 2 to 5 degrees. Why on earth would they do that? Well, it's a brilliant little piece of ergonomic design. Because that rivet is tilted, when you rotate the tab to line it up with the opening, one side of the tab is forced to ride up the slope, and this automatically lifts the end of the tab just enough for you to get your finger under it. No more fighting to pry it up, it does the work for you. And there's even more. Some cans have these tiny ramp-up beads to give the tab an extra lift. There's also a secondary anti-fracture score to make sure the can doesn't burst if the pressure gets too high. And the shape of the opening, sometimes called a shark fin, is designed to let air flow in as you pour, which makes the whole thing much smoother. It's an incredible density of clever thinking in such a tiny space. So let's put all these pieces back together. We've seen how each individual part of the can is its own little masterpiece of optimization. This right here shows just how precise the engineering has to be. Research shows that making the wall just 10 micrometers thicker, again, a fraction of a human hair, increases the can's resistance to being crushed by a whopping 116 newtons. Even the varnish layer on the inside, which is only 5 microns thick, adds a measurable 21 newtons of strength. Every single micron counts. So when you hold a can, what you're really holding is a perfect balance of all these different engineering fields. You've got material science for the impossibly thin walls, physics for the dome's strength, mechanical engineering for the lid's lever system, and even ergonomics for that clever tilted rivet. At the end of the day, this simple object is pretty much the pinnacle of design for its purpose. It finds the perfect harmony between being incredibly strong yet lightweight, ridiculously cheap to make at scale, and just effortlessly easy for all of us to use. It really makes you wonder, doesn't it? The next time you grab a drink, just take a second to appreciate the century of innovation you're holding in your hand, and maybe ask yourself, what other everyday objects are hiding this level of genius, right in plain sight? Thanks for tuning in.